Uh, Thank you, Miko, for giving us such an inspirational talk, and also to Sensofusion for giving us such a challenging task. We haven't slept in 2 days, and I think it's the most fun we've had recently in hackathons. We're Armhampton, and we built Wavelet, a powerful and accurate radio wave sim.
And the challenge we did was the Radio City Challenge, where we used a model of Hong Kong, and we created a simulation to visualize radio waves.
Now, the reason why we picked this challenge was it both gave us a huge set of hard problems in simulation, provided loads of educational value, and let us work on some really cool tech. The entire simulation was written in pure C++, as well as NVIDIA GPUs, OpenGL, and OpenMP. We did not do this because we were masochists, but more so because there was no other pre-existing solution at the time to develop this. Now, the simulation boils down to just some basic physics. We have a simulation initially using these formulas, which boils down to just a 2D for loop. And that's pretty simple to do. And we were able to implement this in some time. Now, the issue with this in 3D simulations is that it has a cubic time and can end up being quite slow. But we ended up making some initial simulations using Maxwell. You can see the simulation right here below. And this simulates the waves and radio signals using Maxwell's. If we go next. And yeah, another benefit of having this level of performance using NVIDIA and OpenGL is we are able to render the millions of vertices, such as from Hong Kong in the data set. Next. Great. Yeah, and we can get radio propagation as well. It is accurate to real-world Maxwell simulations, and we'll be able to see this very soon in our demo.
While I set up the demo, I'm going to have my friend over here hold the mic, because I can't do it one-handed. 1 second. Bear with me 1 second. It's just slow, because my GPU is slow. Cool. So this is our simulation. This is hard to navigate on a massive screen like this, but in theory, the simulation should begin shortly once my GPU learns to deal with it. Give it a second. Give it a second. There we go. So this is a relatively accurate simulation. So this is kind of like an editor plane. You can create nodes as you wish. I would do that right now, but we'd run out of time, so it's not really worth it. This gives you the idea. You can create nodes with various frequencies and things. It has various use cases, so you could use this for simulating Wi-Fi, but we are using Maxwell equations, so it's the entire electromagnetic spectrum. So you could use X-ray or whatever. We just used radio for this case, because that was the task. It's like entirely GPU dependent, but it can run on a tiny laptop GPU like this, so I feel like it's quite scalable as well. And yeah, as you can see, it's quite. We do have better visualizations than this, and it looks quite a lot worse on the projector. But yeah, it diffracts around the edges, and it does interference with each other as you'd expect with any other waves. And yeah, we thought it looked cool, so we made it. Yeah. Yeah, another reason, I think Mona said this earlier, but another reason we made this was because we were looking for existing solutions while we were researching about the challenge, and we found basically nothing. There is no like lightweight tool that can do this. There's like commercial options available made by like massive companies or like MATLAB, but like this is the only thing we could find or make ourselves, so yeah. Thanks for voting for us, I guess. Cool.
Hey, everybody. Hey, guys, quick question from Ryan here. Quick question for you guys. Can you guys quickly tell me what each of you did in the project and how you guys made decisions?
Can you repeat the question?
Can you tell me how each of you contributed to the project?
How each of us? Okay, so I work personally on the research for the algorithms. So originally we were working on a helmet simulation, which is way too slow. We found a way to optimize it and actually get it to work in parallel using OpenGL. And that was my main contribution to it. And
mine and Akshith's contribution was we tried to download Mapbox satellite imagery and actually map textures onto the Hong Kong city. Unfortunately, we weren't able to quite get it to work as we expected, but we still had a damn good go at it nonetheless.
It turns out the curvature of the Earth actually affects what can be mapped onto Hong Kong, given how big the data was.
Cool. So my main contribution was, since I have a low-level background, I was responsible for the whole rendering thing, how we render that many vertices, and how we can optimize it to not kill my GPU. Yeah. Those two worked on the map.
We both worked on the satellite texturing.
Yep.
Yeah. I also shot and edited our video.
So Inga here, super interesting, and I've seen a lot of companies sort of doing various things actually in Hong Kong environment, because it's such a difficult environment for radio signals or indoor positioning or everything. But talk about the real world applications. Where could you use this in simulations? You mentioned it very quickly, but that was like Wi-Fi and a few others, but think one step ahead.
There are a couple. So one good one would probably be with Wi-Fi and Wi-Fi planning, especially with big urban cities. So when you want to find the best Wi-Fi router positions, we were working on something with this where we basically find optimal locations given any kind of area. With something like Hong Kong, where you have really dense concrete and other kind of things in the way, that'll be very useful. Also, the waves aren't limited to just transverse. They also work longitudinal. So you could kind of use it to optimize noise in very busy areas and urban sprawls like Hong Kong, to place things like speakers and whatnot to minimize loud traffic and whatnot.
Another application that we kept in mind was education, because we wanted to keep an accurate simulation instead of one that just looks cool, because you could use it for actual education, right? The physics concepts that children are learning in school, for example, like there are pre-built scenes that we can create and share and whatever. Anyone can load them, anyone can run them. So the idea is, if a child learns a concept in school about waves, they should be able to simulate it and run it and like view it as it is and see the results in like to help them to learn.
Super.
Hi, thanks so much for the pitch. I'm Aino. Maybe my follow-up, actually, what Inga asked is that, like, now mentioned about different kind of like possible implementations. Like now, if you would have like, I don't know, next like 48 hours, like what direction you would actually like start taking the product, and like what is the most valuable or impactful like use case you would actually like start taking this towards to?
So one of the main ideas that we had, as Rono said, that we didn't really get around to implementing was the whole planning aspect of it, right? So the idea we had was we would be able to map out a region where we were like wanted a strong signal, for example, and it would algorithmically map out the best possible locations that are feasible and like not in a building, for example, to like get the maximum like signal strength to a given region.
Keanu and Aki were working on this, but mapping textures, such as what you saw in simulation was just the gray buildings and a gray ground. In reality, we'd have concrete, glass, all sorts of other textures and materials. Since sound and any kind of radio waves pass differently through these kind of materials, it would make our simulation much, much more accurate. Anybody else? No? Yeah, I think that's about it.
All right. Let's give a hand for Wavelet.